Hello, hi everyone. Welcome to the Student the Brand. This is our Siva sir. Today we are going to discuss about magnetic effects of magnetic effects of electric current. Magnetic effects of electric current. So, what is the meaning of magnetic effects of electric current? When the current is passing through the conductor, when the current is passing through the conductor acts, the conductor produce, the conductor behaves as a magnet. Okay, so it acts as a magnet. So that is called magnetic effects of electric current. Sir, I have one question, sir. So what is magnet? The substance which can attract the magnetic material, the substance which has the property of attracting. Okay, so that is magnet. Understood? Magnetite or lodestone. Magnetite or lodestone. Magnetite or lodestone is a natural magnet. Magnetite or lodestone is called lodestone is called natural magnet. So coming to the artificial magnets, man-made magnets, what artificial magnets? Okay, so what are these artificial magnets? So the substances, the magnets which are made by the humans, those are called artificial magnets. Those are called artificial magnets, right? Yes. So we'll discuss about magnetic properties, magnetic field lines. So generally, if you suspend the magnet, it always shows north and south direction. Okay, it always shows north and south direction. A freely suspended magnet always shows north and south direction. Understood or not? So it always shows north and south direction. Point number one. And coming to the point number two, North Pole will repel. North Pole will repel. But South Pole will attract. And North Pole also will attract. North Pole will repel. And South Pole repel. But South Pole will attract. South Pole and North Pole also will attract. Yes. Right? So, if you suspend the magnet freely, it always shows north and south direction. Okay. So, I am taking the bar magnet. So, which magnet I am taking? Bar magnet. So, here I am considering this is a bar magnet. This is a bar magnet. Okay. So, magnet has two poles. Magnet has two poles. Those are North Pole and South Pole. Magnet has two poles. So those are North Pole and South Pole. Understood or not? North Pole and South Pole. So I am taking here. This is North Pole and this is South Pole. Sir, I have one question. Okay. So what is that question? So how the magnetic field will be around the magnet? The magnetic field will be in the magnetic field will be around the magnet in the form of magnetic field lines. Sir, what are those? Okay, so the magnetic field lines, okay, the field will be in the form of field lines. Okay, so those are outside of the bar magnet, from north to south. And coming to the inside of the bar magnet, south to north. Inside, south to north. Outside is north to south. Outside of the bar magnet, the magnetic field is north to south. And inside of the bar magnet, the magnetic field is south to north, south to north. Yes. Dishka, south to north. Outside, north to south. Sir, how it is? Free north pole of the magnet. Okay. If you place a compass around the magnet, okay, so the direction of the free north pole, represents the magnetic field lines around the magnet. Okay, around the magnet. Understood? So now you can see, so this is the bar magnet. What is this one? Bar magnet. Okay, so the magnetic field lines are north to south. So you can take 5, 7, 9. How many lines you can take? You can take 5 lines, 7 lines, and 9 lines. So it is to represent in a good way, in a clear way, in a proper way, in a visible way, in neat and we can say nice looking, in a clear looking, and if the first impression is the best impression. Like that. If you draw the diagram, you will get good marks. Immediately. Okay, so how to draw a diagram? So north pole to south pole I am taking like this. So how many lines I said? 5 or 7. So 2 lines you can take, and 2 lines you can consider here, and 3 lines in the middle. Like this and like this. So 7 lines diagram. What is one? 7 lines diagram. You can observe here, north pole to south pole, the magnetic field is there. So north pole, so at here, at the north pole, the magnetic field lines will move away, emerging out. Okay. So from north pole, the magnetic field lines are moving out, emerging out. Yes or no? Towards the south pole, the magnetic field lines are reaching. Okay, merging at south pole. From north pole, emerging out. Simple step, no? Then. Like this. Okay, so here to the magnet. So towards south pole, the magnetic field lines are reaching. So at the north pole, the magnetic field lines are leaving. That's how, no? Magnetic field lines are leaving. That is north pole. Magnetic field lines are reaching. That is south pole. Outside of the bar magnet, magnetic field lines are north to south. Inside of the bar magnet, south to north. Understood or not? So here, the magnetic field lines around the bar magnet, north to south. Inside of the bar magnet is south to north. That is the point. And so what is magnetic field? I have one question. Sir, what is magnetic field? The region around the magnet, magnetic field. The region around the magnet in which magnetic force, the region around the magnet in which magnetic force exert, the region around the magnet. See, here you can see within this region, the magnet will attract the magnetic materials within this region. Beyond the region, if you go beyond the region, magnet will attract. Magnet will not attract the magnetic materials within this region. The magnet will attract the magnetic material. That is called magnetic field. Within this region, beyond the magnet, beyond the field, Magnet will not attract the magnetic materials. So within this field, it can influence the magnetic materials. It can influence the magnetic field. If you go beyond it, so more than the magnetic field, no impact, no influence. So that field, that region is called, that field is called magnetic field. Sir, okay, sir. How the field will be around the magnet? As I mentioned, magnetic field will be in the form of field lines. Magnetic field will be in the form of field lines. How the magnetic field? In the form of magnetic field will be in the form of field lines. Yes, will be in the form of field lines. Yes or no? Those field lines are outside of the bar magnet, outside of the bar, outside of the bar magnet, from north to south, inside of the bar magnetic, south to north. South to north. Outside of the bar magnet, the magnetic field lines are north to south. Inside of the bar magnet, the magnetic field lines are south to north. Yes or no? Yes or no? So this is about magnetic field lines. Okay. So second point, these field lines, magnetic field lines, magnetic field lines. Magnetic field lines are closed loops. Magnetic field lines are closed loops. These magnetic field lines never intersect. These magnetic field lines are closed loops, but these magnetic field lines never intersect. Never intersect. Sir, if it is intersect, so if these magnetic field lines, intersect, so what happens? If this line intersects, what happens? What will happen? At the point of intersection, compass should show two directions. Is it possible? Compass will show two directions? Compass will not show two directions at a time. Sir, what is compass? Compass is nothing but a small magnetic needle is present inside of it. Compass is a small magnetic needle present inside of it. Small, it is a magnetic needle. It always shows north and south direction. It always shows north and south direction. It always shows north and south direction. Yes or no? It always shows north and south direction. Okay. So, if these field lines intersect, compass will not show two directions at a time. Okay, agree. But I want one thing. I want to know one thing. That is, so I want to know the magnetic field line direction. I want to know the magnetic field direction. I want to know the magnetic field direction at a particular point in the magnetic field. I wanted to know the magnetic field direction at a particular point in the magnetic field. How can I identify? So there is one point. That is, if you draw the tangent, 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 if you draw the tangent to the magnetic field line along that particular direction. So here you can see along this particular direction. So if I draw the magnetic field line direction, if you draw the tangent, okay, if I draw the tangent, okay, so a line touches the circle or curve at one point. So a line touches the circle or curve at one point. Okay, so if you draw the tangent at that point, so we can identify the magnetic field direction. We can identify the magnetic field direction at that particular point. We know that. What we know that? Outside of the bar magnet, the magnetic field is north to south. Inside of the bar magnet, inside of the bar magnet is south to north. Outside of the bar magnet is north to south. Inside of the bar magnet is south to north. So it is on sequency. So like first light, reflection, diffraction, human in colors word, electricity, magnetic effects of electric current. Likewise, I am teaching. So if you want the chapter, so my previous videos are there. Once you go and check those previous videos, you will get to know. So you want in live class only means, so you have to wait until maybe until tomorrow. So it will be according to the sequence I am teaching the chapters and a practice session too. Okay, so chapter with practice. So practice sessions. Okay, done. So here, if you draw the tangent to the magnetic field line, so along the tangent, the magnetic field will be there at that particular point. First point, magnetic field lines emerge out from north, merge at south. Point number 1. Coming to point number 2. These are closed loops. Magnetic field lines are closed loops. These field lines never intersect. These field lines never intersect. Sir, if it is intersect, so what happens? If it is intersect, so what happens? At the point of intersection, compass should show at a time two directions where it is not possible. Compass will not show two directions. So you can observe here. So this is one direction and this is one direction. I'm drawing the tangent like this, So compass should show at a time two directions. It is not possible. Okay, it is not possible. Understood or not? It is not at all possible. Compass will not show two directions at a time. Okay, so this is about magnetic field lines. So first one, magnetic field, the region around the magnet in which magnetic force exerts. The region around the magnet in which magnetic force exerts is called magnetic field. Okay, so the magnetic field will be in the form of field lines. Magnetic field will be in the form of field lines emerging out from north, merging at south. Outside of the bar magnet is magnetic field from north to south. Inside of the bar magnet is the magnetic field from south to north. These are closed loops. These are closed loops. These field lines never intersect. If these field lines intersect, so what happens? Compass should show two directions at a time. Compass will show two directions at a time where it is not possible. Where it is not at all possible. No, 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 no. No, 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 no. Compass will not show two directions at a time. Compass will show only north and south direction. So what is there inside of the compass? It is a magnetic field. It always shows north and south direction. North south direction. Sir, here one point is, so whatever you said in that magnetic field lines, you said those are closed loops. Okay, outside of the bar magnet, inside of the bar magnet, everything is clear. Okay, if it is intersect, so compass should show two direction. This is not false. So these field lines never intersect. Okay, so here outside of the bar magnet you said, right? So magnetic field and magnetic field lines. So this is about magnet. Okay, so this is about magnet. So understood. Now we'll discuss about one more thing, that is so now we'll discuss current carrying conductor behaves, act as a magnet. Understood? A current carrying conductor produces the magnetic field, behaves as a magnet, act as a magnet. Yes or no? So in lower classes we did on an experiment, that is, so take a iron nail, wrap the copper wire around it like this. So take a iron nail and wrap a copper wire around it, connected to the circuit. If you connect to the circuit, yes, it acts as a magnet. It attracts the magnetic materials. If you connect to the circuit, it acts as a magnet. It attracts the magnetic materials. Yes or no? Yes. So I am taking this straight copper conductor. I am taking a straight copper conductor. So here you can see this is thick copper conductor. I am connecting to the circuit. Circuit. A thick copper straight conductor. So I am taking this one that is connected to the ammeter, rheostat. This is a rheostat. Rheostat is nothing but the device which is used to regulate the current without changing the voltage source. Means without changing the device, it can alter the current. Okay, so here I am considering like this. So current is passing here. You can observe. So this is a magnetic current is passing. Sir, so you said when current is passing through the conductor, it behaves as a magnet. How can you identify the magnetic field around it? By using compass. If you place compass, okay. So compass, as I mentioned, compass is a compass. So inside of the compass, small magnetic needle is present. So this is north and south, east and west. North, south, east and west. Okay. So if you take a straight copper wire, this is like this. So you can take the paper. You can consider the paper over here. Okay. So sprinkle iron particles, magnetic materials. Sprinkle iron particles or magnetic materials around it. If you sprinkle, okay. So it acts as a magnet. We know that it acts as a magnet. Around it, magnetic field will be there. Yes or no? So around the conductor, the magnetic field will be in the form of concentric circles. So making this as a center, considering this as a center, So taking reference this one as a center, the magnetic field will be in the form of concentric circles around the conductor. Around the conductor, the magnetic field lines are in the form of concentric circles. Yes. If it is acting as a conductor, it produces the magnetic field around it. Yes or no? So around the conductor, magnetic field will be produced. Right? Yes. So here you can observe, by using compass we can identify. So here you can observe like this. Sir, I have one question. Sir, you said if the current is passing through the conductor, if the current is passing through the conductor, magnetic field will be produced. You said that, right? But in which direction that magnetic field will be, sir? Sir, you said one thing. When the current is passing through the conductor, it behaves as a magnet. Means magnetic field will be there around the conductor. Right? So, in which direction the magnetic field will be? You said in the bar magnet, magnetic field will be in the form of field lines. Those are outside of the bar magnet is north to south. Inside of the bar magnet is south to north. You mentioned that, right, sir? But in the around the conductor, the magnetic field will be in the form of magnetic field will be in the form of field lines. So those are close concentric circles. You mentioned that one, right? I can understand. But the thing is, in which direction the magnetic field will be? In which direction the magnetic field will be? So by what rule we can identify the magnetic field direction? Magnetic field direction by using right hand thumb rule. By using right hand thumb rule, we can identify the magnetic field around the current carrying conductor. If the current is passing through the conductor, if the current is passing through the conductor, by using right hand thumb rule, we can identify the magnetic field direction. Place thumb along the current direction. Place the thumb along the current direction. Curly fingers, folding fingers, folding fingers shows the magnetic field direction. So along the thumb. So along the current, thumb you have to place. Along the current, carrying conductor, current direction. Okay, along the current direction, you have to place the thumb. And folding fingers shows the magnetic field. So if you place the thumb along the current carrying conductor, curly fingers, folding fingers, folding fingers represent the magnetic field. Yes, curly fingers, folding fingers represent the magnetic field around the conductor, around the current carrying conductor. Yes or no? So if you place the thumb along the current carrying conductor, curly fingers, folding fingers, wrapping fingers shows the magnetic field. Right? So that's enough. By using what rule? Right hand thumb rule. By using right hand thumb rule, we can identify the magnetic field direction. Around a current carrying conductor. Magnetic field direction can be identified by using right hand thumb rule. Right hand thumb rule. Right hand thumb rule. Ah, okay. Right hand thumb rule. Right hand thumb rule. Right hand thumb rule. Okay, so if the current is passing from north to south, if the current is passing from north to south, if the current is passing from north to south, curly fingers, folding fingers, wrapping fingers, curly fingers, folding fingers, wrapping fingers represent magnetic field direction around the current carrying conductor, around the current carrying conductor. If the current is passing from south to north, if the current is passing from south to north, curly fingers, folding fingers, curly fingers, folding fingers represents the magnetic field around the current carrying conductor, current carrying conductor. Understood or not? So if the current is passing like this, if the current is passing like this, if you place thumb along the current carrying direction, curly fingers, folding fingers, wrapping fingers shows magnetic field direction, magnetic field direction around the current carrying conductor, current carrying conductor. Yes or no? Yes. So this is about right hand thumb rule, right hand thumb rule, right hand thumb rule, right hand thumb rule. Understood or not? So this you have to keep in mind. Keep in mind. So next one. So here you can observe this is the conductor. This is the conductor. So if the current is passing from north to south, magnetic field will be like this. If the current is passing south to another, magnetic field will be there. So you can observe here. This is the magnetic field direction. Like this. So near to the conductor, magnetic field is more. Near to the conductor, magnetic field is more. If you move away from the conductor, near to the conductor, magnetic field is more. If you go away from the conductor, magnetic field is less. If you stand near to the fire, we'll get. If you hold the ice cube, oh my god, you can't able to hold it, right? So near to the conductor, magnetic field is more. Near to the conductor, magnetic field is more. If you move away from the conductor, magnetic field is less. Magnetic field is less. And also one thing. Magnetic field is directly proportional to the current flowing through the conductor. If more current is passing through the conductor, if more conductor is more, if so max if now if strength of current is more, if current is more, then magnetic field also increases. Yes. If current is more, so one cell current, two cells current increase, three cells current increase, four cells current increase, five cells current, six cells current, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 7. If it is continuous, current is increasing in the conductor, right? Magnetic field also increases. Means magnetic field is directly proportional to current flowing in the conductor. Yes. So that's enough. And next one. So we can take, so near to the conductor magnetic field will be more. And one more thing, more crowding of magnetic field lines represent. If more crowding, okay, so if you drop the magnet into the sand, if you drop the magnet into the sand, the magnetic materials will attract more at the ends. Did you observe any time? Do you observe any time that point? The magnetic field lines are more at the poles because magnetic field will be more at the poles than in the middle. Means crowding of magnetic field lines represent, so more magnetic field lines represent more magnetic field, field lines are crowded magnetic field lines represent more magnetic field, right? Less magnetic field represent less magnetic field, more magnetic field represent more magnetic field, less magnetic field represent less magnetic field. What about medium magnetic field lines, sir? Medium magnetic field, that's enough, right? So if number of turns increase, that I will explain. So in the solenoid case, so next one, loop. So here one is, if the current is passing, it act as a magnet, magnetic field will be produced around the conductor, magnetic field will be in the form of field lines, magnetic field will be in the form of field lines. Okay, so around the current carrying conductor, the magnetic field will be in the form of concentric circles. Okay, near to the conductor more magnetic field, away from the conductor less magnetic field. Okay, yes, that is very very important. Next one you can see by using compass. Okay, if you place the compass near to the current carrying conductor, gets deflected. Yes, if you place the compass near to the current carrying conductor, suddenly it gets deflected. Okay, so if you place the compass near to the current carrying conductor, boom, 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 suddenly it gets deflected because magnetic field will be there around the conductor. Magnetic field will be there around the conductor. Yes or no? Hans Christian Ørsted. Hans Christian. Aman, thank you. Arman, thank you. Hans Christian Ørsted. Hans Christian. Hans Christian Ørsted. Given the relation between Hans Christian Ørsted, given the relation between electricity and magnetism. So a compass is placed near to a current carrying conductor, suddenly gets deflected. So it's got deflected. So by observing that, he given that relation. There is a relation between electricity and magnetism. Understood or not? Oh, thank you so much. Oh, ICSE student. Okay, so here, what is that? Hans Christian Ørsted given the relation between electricity and magnetism, right? Yes. So this is the straight current carrying conductor. A straight current carrying conductor. Understood or not? Yes. And one more thing. So there is a loop. Come to the point. So just now I took the straight conductor, right? So just I took the straight conductor, straight conductor, straight conductor. But if I, this time I'll take a loop. So copper wire, so bent in the form of, bend the copper wire in the form of loop, in the form of loop, in the form of loop. Yes or no? Then it will be like this. Like this. This is plus and minus. If the current is passing, we know that current carrying conductor behaves, behaves as, produce the magnetic field, behaves as a magnet, and exhibit the magnetic properties. Magnetic properties. Magnetic properties. Yes. Now, if the current is passing through the loop, if the current is passing through the loop, magnetic field will be produced. Yes, magnetic field will be produced. How the magnetic field will be? How the magnetic field will be? You tell me how the magnetic field will be there. It will be in the form of, check here. I am checking here so you can observe. So you can observe. At the center, the magnetic field lines are parallel lines. At the center, the magnetic field lines are parallel lines. Sir, I have one question. Sir, I have one question, sir. The question is, sir, so where, in which place the magnetic field is more in the loop, sir? In which place? Where? Exactly where the magnetic field is more in the loop? At the center or circumstance? At the center or circumstance? Sir, please tell me, sir. So where the magnetic field is more, sir? At the center or circumstance, sir? Sir, where the magnetic field is more? The magnetic field is more at the center. Why? Why? What is the reason? Why the magnetic field is more at only at the center? Why can't at the circumstance? Yes, tell me. Why can't it be at the circumstance? So here, these are the circumstance, right? Yes or no? So why only you're saying the magnetic field is more at the center? Magnetic field is more at the center, right? How it is possible? How can you say like that? Right? So here you can see, by using right hand thumb rule, by using right hand thumb rule, by using right hand thumb rule, we can identify the magnetic field direction. Yes or no? By using right hand thumb rule, we can identify the magnetic field direction. Yes or no? If the current, along the current carrying conductor, if you place the thumb, the curly fingers, folding fingers, wrapping finger represents the magnetic field. Right? Yes. Understood. So that's why this is north and this one is south. You can observe the field is moving out. The field is moving out and reaching to here. Understood, Anna? The field lines are moving out and reaching to south. And one more thing, you need to understand one thing. You have to understand one thing, that is, you have to understand one thing, that is, so at the center the field lines become parallel lines. At the center the field lines became as parallel lines. Yes or no? Became as a parallel lines, right? So one magnetic field will be added up to another magnetic field. Do you know tug of war? Tug of war. People at one team and people at another team, they will hold the energy. They will add up the energy to one person to another, one person to another. Then the strength will be more. Okay, so equal strength. Here also, the magnetic field will be added up to one to each other. Then at the center, magnetic field will be more. Okay, so than compared to the circumstance. This is the loop. This is the loop. Understood or not? This is the loop. Sir, what about solenoid, sir? What is solenoid? So I'm getting lot of confusion, and sir, one more thing is, how can you take the directions? So some people, they will say you wrap like this. Some people will say wrap like this. So copper wire, insulated copper wires. So they will say you have to wrap like this. If you connect to the circuit, it acts as a magnet. Some people, they will say like this. Okay. So how to take the directions, how to act, and what is the difference between solenoid and bar magnet? What is the difference between solenoid and bar magnet? Solenoid and bar magnet. We'll discuss, right? Yes. So this is the loop. Now we will discuss about solenoid. Insulated copper, insulated copper wire, wrap in the form of cylindrical shape. Insulated copper wire wrap in the form of cylindrical shape. So take a straight copper wire, insulated copper wire wrap in the form of cylindrical shape. Wrap in the form of cylindrical shape. Connect to the circuit. Connect to the circuit. Current will pass in the solenoid. When current is passing through the conductor, it behaves as a magnet. When the current is passing through the conductor, it acts as it behaves, or it produces magnetic field. Sir, so you said, so I'm taking the loop like this, and connect to the circuit. So positive terminal, negative terminal, current is passing. Yes or no? Current is passing positive terminal, negative terminal. So the magnetic field will be here, right? Magnetic field is there. So at the center, understood or not? So you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 lines. There are 9 lines. 3 lines you have to connect. Three lines you have to connect here. Three lines you have to connect like this. Three lines you have to connect like this. And three lines you have to connect downward. Yes, you have to connect remaining three lines like this. Like this. And like this. So remaining three lines. Remaining three lines. Like this. Current is reaching to this side and current is leaving this side. Okay. Current is reaching to the side and current is leaving to the side. Like this. Here you can see current is leaving. Leaving. That is north. If the current is leaving, magnetic field also leaving. Yes or no? Yes. And here also current is reaching, magnetic field also reaching to this point. That is south, north and south. And here you can observe outside of the solenoid is. Sir, I have one question. Sir, I have one question. What is that? Sir, I have one question. I have one question. I have one question, sir. I have one question, sir. What is that? The question is, so here you can observe the magnetic field will be around the solenoid from north to south. Inside of the solenoid is south to north. Sir, sir, what are the differences between solenoid? What are the differences between solenoid and bar magnet? What are the differences between solenoid and bar magnet? Point number one. Remember, very important. Keep in mind. Very important. Very important point. Solenoid act as a magnet. Solenoid act as a magnet. Bar magnet also. Bar magnet. Yes or no? So magnetic field will be same. Around the solenoid, north to south, south to north. But here is one difference. That is, here is one point. In the solenoid, we can increase the magnetic field. Yes. How can you increase the magnetic field? How can you increase the magnetic field? How can you increase the magnetic field? By increasing the strength of current. By increasing the strength of current. Point number one. Coming to point number two. By increasing strength of current, the magnetic field will be increased. By increasing number of turns. By increasing number of turns. By increasing number of turns, we can increase the magnetic field. We can increase the magnetic field. By increasing the strength of current, we can increase the magnetic field. By increasing the number of turns, number of loops, we can also increase the magnetic field. We can also increase the magnetic field. And one more point. Solenoid is a temporary magnet, whereas bar magnet is permanent magnet. north, south. Bar magnet, bar magnet, bar magnet, bar magnet, bar magnet. Bar magnet is permanent magnet. Bar magnet is a permanent magnet. Solenoid is a temporary magnet. Temporary magnet. If you remove the battery, if you remove the battery, solenoid will not behave. It does not act. It does not show the magnetic properties. Magnetic behavior it does not show. Only when you connect battery, if you add number of cells, magnetic field will be produced. If you remove the battery, it does not produce magnetic field. It does not act the magnetic, it does not exhibit the magnetic behavior. Understood? Is it clear? Solenoid is a temporary magnet. Bar magnet is a permanent magnet. Ah, ah, ah. I hope it is very clear. All right? Yes. So next one is, so here you can observe, will you able to change the bar magnetic poles? Will you able to change the bar magnetic poles? Can we change? Can we interchange? North to south, south to north? No, not at all possible. Not at all possible for solenoid. Sorry, sorry. For bar magnet. For bar magnet, we can't able to change the poles. For bar magnet, we can't able to change the poles. But solenoid, we can able to change the poles. How can you change? By changing the magnetic field direction, by changing the current direction. If you change the current direction, magnetic field direction also changes. As I mentioned earlier, as I mentioned in the earlier class, if the current is passing upward direction, the magnetic field, curly finger represent, folding finger represent magnetic field. If the current is passing downward direction, curly fingers, folding fingers represent magnetic field. Right? So if you change the battery direction, that is nothing but if you change the polarities, positive terminal, negative terminal, if you change the current direction, that's enough. If you change the current direction, the poles of the solenoid also changes. Magnetic field direction also changes. That's enough. What are the points we discussed till now? Point number one. So solenoid act as a bar magnet. Magnetic field will be there around the solenoid. That to north to south outside, south to north inside. Point number one. Coming to point number two. That is, we can increase the magnetic field. We can increase the magnetic field by increasing strength of current, by increasing number of turns, by increasing strength of current, by increasing number of turns. So strength, more current if you send, so more magnetic field will be there. If you increase the number of turns, Number of turns, number of turns, number of turns, number of turns. If you increase the number of turns, the magnetic field also increases. Magnetic field also increases. Yes. Right? Understood or not? Is it clear or not? Yes. That's enough. That's enough. That's enough. That's enough. Understood or not? I hope it is very clear. Yes. That's enough. Understood or not? I hope it is very clear. Next one. Next one. Next one we will discuss about one more. One more. That is solenoid and bar magnet is completed. Now we will discuss about current carrying conductor placed in the external magnetic field. A current carrying conductor placed in the external magnetic field experience a force. Let's solve. Come to the point. So, are you understanding or not? A current carrying conductor, a current carrying conductor placed in the external magnetic field experience the force. Force, experience the force. Experience the force. A current carrying conductor placed in the external magnetic field experience the force. Experience the force. Understood or not? Right. Come to the point. So I'm taking your turn, 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 turn. Turn, 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 turn. Turn, 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 turn. So stand. 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 Okay, this is the stand. 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 So I'm taking the stand like this. Okay, this is the stand. A current carrying conductor experience C. If you place this a current carrying conductor A, B, so current is passing and you, so it is placed in the external magnetic field. So here you can check. So this I am taking here. This the U-shaped magnet, that is north south, and here I am connecting like this. Positive terminal, negative terminal, current is passing like this. Yes or no? Current is passing through the conductor placed in the external magnetic field. That is horseshoe magnet. Horseshoe magnet. So the force will act on the conductor. Force will act. Yes or no? Force will act on the conductor. Sir, by using what rule? By using what rule, we can identify the, by using what rule? Based on what rule you can identify the force acting on the conductor? How? How can you say like that? Force will act. How it will act? In which direction it will act? Which rule will use? What rule is that? What is that rule? What is that rule? What is that rule? What is that rule? That rule is Fleming's left hand rule. That rule is Fleming's left hand rule. By using Fleming's left hand rule, we can identify By using Fleming's left hand rule, we can identify. So index finger shows the magnetic field. Index finger shows the magnetic field. And the second finger, middle finger represents the current direction. And thumb finger represents the thumb finger represents the force acting on the conductor. Force acting on the conductor. Index finger represents the magnetic field. Index finger represents the magnetic field. So middle finger represents the current direction. Thumb finger represents the force acting on the conductor. Force acting on the conductor. Yes. So place. Current is passing magnetic field. Current is passing magnetic field. Which direction thumb is showing? Which direction the thumb is showing? Inward or outward? Inward direction. Into the board, into the page. Yes or no? So current is passing. So index finger shows the magnetic field. North, south, current is passing. If you take the thumb finger represents the force acting on the conductor. Thumb finger represents the force acting on the conductor. Thumb finger represents force acting on the conductor. So place like this. Okay. So place like this. So thumb is showing into the board. Thumb is showing into the board. Into the board. Understood? Check once. Understood or not? Check once. Thumb is showing into the board. Into the board. So like that you have to take. Okay. Right? Understood or not? I hope it is very clear. I hope it is very clear. So this is about a current carrying conductor placed in the external magnetic field. Experience the force. Experience the force. A current carrying conductor placed in the external magnetic field. Experience the force. By using Fleming's left hand rule. 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 We can understand. We can understand the force acting on the conductor. Force acting on the conductor. Understood or not? Understood or not? We can understand the force acting on the conductor. This is called Fleming's left hand rule. Fleming's left hand rule. I hope it is very clear. So coming to short circuit, oh my god, if you're taking this is a negative terminal, this is a positive terminal, the direct contact of live or neutral takes place. If there is no insulation on the wires, the direct contact of live or neutral takes place, then heavy amount of current will be drawn from the mains. Then fire will occur in the building. Right? Yes. If you connect all the appliances, high voltage appliances, if you connect all the appliances, so if you connect high voltage appliances at a time to the socket, then heavy amount of current will be drawn from the mains. High voltage appliances, if you connect, point number 1. So Second one is, so it may leads to, it may leads to the short circuit. It may leads to the short circuit. High voltage appliances connect, okay, at a time to the circuit, then heavy amount of current will be drawn from the mains. It may lead to the short circuit, right? So positive terminal is red. So red. Positive. Negative terminal. Positive terminal is in red in color. Negative terminal is in black in color. Okay. So we can say. So overloading. That is overloading. High voltage appliances connect at a time. Okay. So heavy amount of current will be drawn from the mains. That is overloading. It may leads to the short circuit. It may leads. Okay, so and what happens? Sometimes insulation may tow, then direct contact on neutral wire and live wire, direct contact takes place. Then heavy amount of current will be drawn from the mains. Understood or not? Yes. Overloading means high voltage appliance. Short circuit means direct contact of live wire and neutral wire takes place. Sometime insulation may tow. Right? So live wire, red color. Coming to neutral wire, live wire. Second one is neutral wire. Neutral wire. That is second one is neutral wire. Neutral wire. That is black color. Coming to the earth wire. Earth wire is green color. Earth wire is green color. Earth wire is. So third one is earth wire. Earth wire. Green color. Understood? So the potential of live wire is 220 volts. The potential of neutral wire is 0 volts. Potential of earth wire is 0 volts. The potential difference between live wire and neutral wire is 220. The potential difference between live wire and neutral wire is 220 volts. The potential difference between neutral wire and earth wire is 0 volts. And the potential difference between live wire and earth wire is 220 volts. So you have to understand one thing. The potential difference between live wire and neutral wire is 220 volts. The potential difference between live wire and earth wire is 220 volts. And the potential difference between neutral wire and earth wire is 0 volts. The potential difference between neutral wire and earth wire is 0 volts. Okay? I hope it is very clear. Understood or not? So this is about magnetic effects of electric current. Magnetic effects of electric current. A current carrying conductor produce, behave or act as a magnet. That is called current carrying conductor. So magnetic effects of electric current. Current carrying conductor produce or behaves or act as a magnet. Okay. So I hope it is very clear. So this is about magnetic effects of electric current. So if you understand, so do like, share, and subscribe to Student the Brand. So this is your sir from Student the Brand. If you like the content, if you like the explanation, if you like my channel, please do like, share, and subscribe to Student the Brand. Inform to your friends, ask your friends to join to the class. Spread a one word regarding the class. Okay. So I hope it is very clear. Thank you so much for joining and attending and listening my class. And again, we'll start at 10:30. Again, we'll start the class 10:30. So at that time I'll come with a different topic. So be ready at 10:30. So we'll see in the class again with a different topic. So do like, share, and subscribe to Student the Brand. So thank you so much. We'll see in the next class. So thank you.